Okay, let's get started. So I did put the quiz grades in from last time. I was just going to pass those around if that's okay. Anyone have any objections to that?
No.
Sure? And some people are like, I don't want people to see my grades. Everyone's all right with that? You sure? All right. So just find yours in the stack and then pass the stack around, please. All right, so we started the chain rule last time, right? We're going to finish that up. We're going to do a couple of examples, and then we're going to do a word problem, and then we're going to move into the next section.
We have our next exam on Monday?
I think we are close, right? The 15th, yep. So let's see what we can get done. That means next class I'll have some sort of review, okay? There is a chance we might push the exam one day, but we'll see. Let's just see how things go here. What's that? No? Okay, so last time what we talked about was the chain rule. And we said that if we have a function f of x, which happens to be some function raised to a power, then the derivative of this is equal to this. And the formula is kind of ugly when you look at it, but in practice, I think it works out a little bit better than the formula implies in terms of the difficulty. So as an example of this, let's say we had 3x squared plus 4x plus 1, let's say to the 8th power. Then if we want to try and see how this is the chain rule, we would have to first see that we have some function raised to a power. So does everyone see that? Like here's the function we have, g. This is our g function. This is like the g of x. And it's being raised to the 8th power. Now is it okay that I'm using brackets here instead of parentheses? It's the same thing?
Yeah.
Okay. So the derivative of this, what we're going to do is first we're going to use that same power rule that we've used in the past. We're going to take the power, we're going to bring it down, we're going to subtract 1 from the power. And the g here, we're not going to touch it, right? We're going to leave it alone. So in that case, it's going to be what here? 8. Then in parentheses, right? Everything stays the same. 3x squared plus 4x plus 1, and then to the 7th power. But that's not the end. Okay, the chain rule says now you have to figure out what the derivative of the inside g function is, and we're going to attach it with multiplication. So we're just going to slap onto the end of this times now the derivative of this. And that, yeah, 6x plus 4, right? Now, very important here that we put this in parentheses, right? Because we're multiplying everything. And if you don't put parentheses, see, look, if you don't put parentheses, then it really means all of this times 6x, then plus 4. And that's not what it is. It's all of this times all of that. So that would be okay. You could just leave your answer just like that. I'd be happy with that. Okay?
The other step was to multiply this side times the 8, right?
You could bring this side over here and multiply it times 8, which would give you, let's see, 8 times the 6, 48x. 8 times the 4, which is 32. You could do, like, pass the 8 through here, and then still have 3x squared plus 4x plus 1. The thing is, you can't multiply the 8 into here because it's to the 7th power, so you can't do that. So you could do that also. Either one of these would be fine. Yes?
So like in our homework, it said
Uh-huh.
with the question mark to replace it with an expression. The
Mhm.
expression was just for the derivative of the g.
For
Like not,
yes, that question mark was wanting you to input that piece right there. It just really wanted to stress that with the chain rule, you have to attach that derivative of this into it. Okay? Does that answer everything then? We're good? So I'd like to try something else.
oh, wait. Question. How do we get the 40?
We don't have to.
You don't have to, but what I did was I multiplied the 8 through here and here.
Oh, okay.
But you don't need to do that, but you could.
Yes, sir.
Okay, I don't need this. Okay, let's do another example. How about this? F of x equals 4 over the square root of 7x plus 1. So you might at this point be thinking quotient rule, maybe, because we have division, don't we? We have a quotient. However, this is a constant, right? And we remember that whenever we have constants in front of functions, when we take the derivative, it just comes for the ride, right? So I'd like for us to start out by not taking the derivative, okay, but by rewriting this problem. So tell me if you agree that this is the same thing. Is that the same thing?
Yeah.
Yes? That's what the square root means, right? Raising it to the 1/2. Now watch the next step. Still not taking the derivative. Is that the same?
Yes.
Yeah, right? Because having a fractional power in the denominator, I could move that up to the top and make it a negative number. Usually when we use the rule, we take negative exponents and drop things down. I'm going backwards and bringing it up. Yes?
I just want to reiterate, so whenever we bring the exponent up that's over a fraction, it's always going to be negative. So
It'll always become negative.
So if it's like a 2 right there, it'll be -2.
Yep.
3 would be -3.
That was 3, that'd be -3, exactly.
Actually,
Yep.
I thought whenever we did the one-time example, I thought it was like it's always going to be -1/2.
Nope, it'll always be negative of whatever the number is. Yeah.
So we can use that on any case with the square root on the bottom?
Yes, you could bring it up. Now, at this point, we're going to take the derivative, but I just want to point out to you, we do not need to do a product rule. I mean, do y'all see that that's multiplication right there? We don't need product rule, and the reason why is because this is a constant. And we already said constants in front of a function, they come for the ride, yes? Now, if this was 4x, we would have to do a product rule. We'd have to do the product rule, that ugly thing, okay? But because it's just 4, I'm just going to bring it for the ride. So I'm ready to take the derivative. So here comes the 4, just comes for the ride. And then now, do you all see? That's your g of x, right? That's your g of x. That's being raised to a power. So we're going to use first part of the chain rule says take the 1/2, bring it out, right? So what's going to pop out front there? -1/2. I'll stick with fractions. You could put a decimal, but I'm going to stick with a fraction. Okay, so -1/2 comes out, and then what do I put? Everything stays the same. 7x plus 1. Now, to what power?
Would it be -3/2?
-3/2, or -1.5. Right, because you're subtracting 1 from this. So that becomes -3/2. Okay? Are we done?
No.
No.
You still have to times it by 7.
Times it by the derivative of this, which is just 7. And I don't need this in parentheses because it's just one term. That makes sense? I thought I saw a question. Oh.
No, I was just going to ask like why didn't
Now, I'm going to clean this up a little bit, all right? I'm not quite done because I've got a bunch of numbers, and I can put numbers together. So I'm going to do this, and this, and this together. So these two together give me -2, right? Half of 4 is 2, but negative times a positive is negative. So that's -2, and then times 7. So -14, 7x plus 1 to the -3/2. We still agree with that? Okay. That's fine as an answer, but I'm going to go one more step. And I'm going to drop that thing back down. Okay, so this was a negative power, so I can drop it back down as a positive power.
Either are fine.
Either are fine, except if you have to plug a number into this, like, because we're going to do that in a second, you want to make sure on your calculator you can do this, right? Because you got to raise something to a fractional power. So we're going to practice on our calculators, make sure you can get that number to come out correctly. Are there any questions on that? All right. All right. Let's do one more, and then we'll do a word problem. How about if we do h of w equals -1 over w cubed plus w squared to the 5th power. And I want us to find dh dw. So I'm using some of that other notation from last class. This was the Leibniz notation. This is really just asking for the derivative of this, right? It's saying, hey, find the derivative of h with respect to w, meaning w is your variable in the problem. So what are we going to need to do first? Move the bottom to the top, right? Move that w cubed plus w squared to the 5th power. Move it up. So I'm not taking derivative yet. And I'm going to write that as -1, and in parentheses w cubed plus w squared to what power? -5. And now at this point, can we go ahead and take the derivative? Yeah? That -1 okay? It's just going to come along, right? So now our derivative, I'm going to write it this way. dh dw equals, we have the -1 coming for the ride. Now what? -5, right? We're going to wind up multiplying these two numbers. Then
-3w to the second
to
to -6.
-6, right? Just be careful on that. You're subtracting 1, right, from a negative number, so you're going to get -6. And we're not done, right? Right? We're not done? Times
3w plus 2w.
3w plus 2w, right?
Yep.
So that was us, sorry, over there, taking the derivative of that g function, putting it here, and having to put it in parentheses because we have two terms. Questions on that? You sure?
Be able to multiply -1 times -5, just make it 5.
I'm going to make that 5, and just for fun, because we're really having fun, I'm going to put the 5 in here, okay? I'm going to just multiply the 5 into this. So we'll have these two together are 5, and then that 5 goes into here. So what do we got there? 15w squared plus 10w. And then we still have w cubed plus w squared to the -6, like that. Now, could I take this whole expression and drop it down as a 6 to the 6th power? Yeah, I could, right? Questions? You right? Right?
Well, if you did drop it down, would you w2 cancel out with the top?
Let me go ahead and do it. If I drop that down, w cubed plus w squared, all to the 6th power, right?
Yeah.
Are you like that, you mean?
Yeah, I must be forgetting this stuff.
Yeah, you can't, because it's 6th power, you can't, and even if that 6th power wasn't here, because you've got pluses between these, you can't do it. So that would probably be like the cleanest answer that we would get, but this is acceptable. This is acceptable too, but you know, if you have two numbers that you can multiply together, go ahead and multiply them together, you know. All right, questions? All right? Ready to do a word problem? Of course you are.
So
Yes.
the process that we're going to end up the way exactly what we're
Every problem is a little different. On the ones I just showed you, yes, that's what's happening, but not every problem. Okay, here we go. Word problem. So we have the total cost in hundreds of dollars. Oops. For producing X cameras per week. So we have a company, we make cameras, all right? And we've come up with a function that gives us the cost. Now, cost being, you know, our employees' cost, the electricity for the building, the rent for the building, whatever it is, right? All of our costs are somehow a function of how many cameras we produce, all right? And here's the actual function. C of X is 6 plus the square root of 4x plus 4. And here x must be between 0 and 30. Now, I haven't asked you any questions. I'm just presenting the information. So let me ask you a quick question. It's not really related. The homework's not going to ask you anything like this. But what is C of 0 equal to, and what does it mean? Okay, so what is C of 0? So you just plug 0 in, right, for x? Get 6 plus the square root of, let's see, 4 times 0, that's 0, right?
2.
Plus 4, so that's 4. So this is 6 plus 2, which is 8, right? So what does that mean?
No less than 8 things that cost you $8.
Okay, so if we make 0 cameras, right, how much is it going to cost our company? $800, right? Because this is measured in $100. So if we don't make any cameras, we still have to pay $800 for whatever fixed costs, things like rent and you know. All right. So we need to make some money. You know, we need to make some cameras to sell them, right? So here's the question that I want to ask. Find part A. Find C prime of x. B, find C prime of 24. C, find C prime of 42. In part D, interpret the answers from part B and C. So I want us to just discuss what the answers represent. Oh, by the way, what was that 0 less than or equal to x less than or equal to 30? What was that all about? What is that telling us?
That's the hit.
It has to be between 0 and 30.
Yeah, so this is telling us, look, our company, we know that we can only produce between 0 and 30 cameras per week. Okay? Like we already know, like we can't make more than 30 cameras a week. Like that's just the limitations of our company. So we have a model of our cost that is valid as long as we're talking about, you know, this number of cameras. Of course, if we buy, you know, hire more employees or buy new machines, whatever, then maybe our cost function is a little different. Okay, so part A, what do we do to get part A? Take its derivative, right?
Correct.
So how are you going to take this derivative? Yeah, put this 4x plus 4 in parentheses and raise it to the half, right? Okay, so let me first rewrite the function. Our cost function is 6 plus 4x plus 4 raised to the 1/2. Now, I have not taken the derivative, right? Just rewriting it in a way that I can take the derivative. So now the derivative. Just about to ask you the same question. Does the 6 come for the ride?
Yeah. Not if it's going to a prime.
I think it's going,
So what's going on in between the 6 and the parentheses? Addition, which means you do the derivative separately, right? Now, if it was multiplication, the 6 would come for the ride. But because it's addition, you're going to take derivative of this one and derivative of this one separate. So derivative of 6 is 0. So it's gone, all right? So that 0, I'll even put it here, 0 plus. Now, on this one, that's going to be what? How do we take derivative of this?
Put the 1/2.
Half out front. What's that rule called again? It is power rule, but we also have a G in here. So that's chain. That's the chain. Chain is like power, kind of, all right? So the 1/2 will come out. We'll have what in the parentheses? What goes in here?
Stays the same.
Stays the same. 4x plus 4. And then we're raising that to what power?
3 and 2.
Careful, it's positive 1/2, right? So we're subtracting 1 from that. 1/2 minus 1 is the same as 1/2 minus 2 over 2, which is the same as negative 1/2. So you have to do a little bit of that arithmetic there. You get negative 1/2 there. Okay? Are we done? No, we're not. Times what?
times 4.
Times 4. Don't need it in parentheses, right? Because derivative of this right here, that's 4. Derivative of that's 0, so we just get 4. Since it's a single term, just leave it here. Now that 4, I can move it out in front with the half, can't I? And half of 4 is 2. So this is really 2, and then 4x plus 4 to the negative 1/2. And we could leave it like that, but again, getting back to what we need to do on our calculators, it might be easier for us at this point to rewrite this as 2 over, so that 2 is staying here. This goes down to the bottom, right? Becomes 4x plus 4 to the positive 1/2 this time. And that is really, if I go back to the other notation, is really the square root, right? Because it's 1/2. If this was 3/2, then no, we couldn't do this. But because it's 1/2, I can go back to this. So there's our derivative, right? That's the answer to part A. Let's now find the answer to part B. I think I'll squeeze that in right here. For part B, all we want to do is plug in 24, right? We're plugging in 24 into, which one? The derivative right here, right? Not the original function. If we plug 24 into here, that would tell us the cost of making 24 cameras, right? That's not what we're looking for. We're looking for this. So this is going to be 2 over square root of, see, 4 times 24 and then plus 4. Let's figure out what that, 4 times 24 is what, 96?
Plus 4.
Plus 4 is 100. Oh, they made it nice for you, didn't they? 2 over root 100, and the square root of 100 is 10. So 2 over 10, which is 1/5, which if you do a decimal is 0.2. Doesn't matter. Take 1/5 or 0.2, either one. That all right?
$20 per camera.
Yeah, so let's try and understand what this represents. But you know what? Let's get part C, and then we'll interpret both answers for part D. All right? But can I ask you this? Maybe this will ring a bell here. Our derivative, right? Our derivative at 24 is 0.2. 0.2 is a positive number, right? 0.2 is positive, which means that the slope of the tangent line is pitched up, isn't it? Which means if we make 24 cameras, it looks like our cost is increasing, isn't it? All right, let's do part C. The derivative at 42 equals 2 over the square root of 4 times 42 this time plus 4. 4 times 42? 160. 168 plus 4? 172. So 2 over the square root of 172, and 172 is not a perfect square. So you're going to have to do that on your calculator.
How many decimal points do you want?
Let's just go like 2 decimal places.
Is that going to be a test, or are you going to write down how many?
I won't tell you, but let's always just go about 2. Yeah, unless I say otherwise. 2 over, what's root 172? 13.11, something like that? So then 2 divided by that, and let's get a decimal.
Uh, 6.5.
6.5, no, I think you did it backwards. 2 divided by 13.11. Should not be getting 6. You should be getting point something. What do you get? 0.152, something like that? Okay, let's just say 0.15, okay, approximately. All right. We all right with that? Now, part D, let's interpret the results. Now this part, what I'm going to do is I'm going to try and help you understand this part by showing you a picture. Not a big picture, but we have a graph. We have x here, and we have c of x here. This right here is, I'm talking about this function right here, right? This is our cost in hundreds of dollars, right? I'm going to put hundreds of dollars. That's the y-axis. The x-axis is what? What is this? What does x represent? The number of cameras we produce per week, right? So x is the number of cameras per week that we produce. All right. Now, we have a graph in here, whatever. The graph looks like something, all right? What we've done is we've gone to 24 cameras. We've gone here and we have found the slope of that tangent line. What is the slope of that tangent line at 24? 0.2, right? So it's pitched up a little bit. Part D is saying to interpret this result. So what all you have to do is remember that the slope of something, right? Isn't the slope always rise over run? Rise over run, right? Rise over run. Now, our rise is measured in that's our cost in hundreds of dollars, right? That's so our up and down is hundreds of dollars. And our run is number of cameras. So this 0.2 right here, we want to look at that as being 0.2 hundred, I'm just going to put $100. Per means division. Per what?
Camera.
Per camera. All right? So what this is saying is that our cost is increasing at $0.200 per camera at that point. At 24, cost is going up by 0.2. What's 0.200? What's $0.200? Like if I told you I was going to give you $0.200, what is that? 20 bucks. Right? You just take 0.2 and multiply it by 100. You get 20. Yes?
Then why did we do 42 if they can only make 30?
Was it 42? Maybe I wrote it down wrong. Hold on. Oh, I did it wrong. I'm sorry.
Oh, okay.
Yeah, I'm sorry. We'll just change that to like 50. Okay, sorry. I put the wrong number in there. Good question. Yeah. Because I even pointed out that we could only look at 0 to 30, and then I asked you to do 42.
Well, I didn't know if it was like a
No, that would have been tricky. Yeah, that would have been, we can't use the function, and yeah, sorry. That was just an oversight on my part. I think what I did is I grabbed the wrong number from the problem below it. Oh, I did the one above it. I'm sorry. Okay, so this says that if we produce 24 cameras, our costs are increasing at $20 per camera. I'm going to write that down because that's what it means to interpret this. So the interpretation of part C is this. If we produce 24 cameras, our cost is increasing at $20 per camera. Okay, that's what part C is telling us. Now, what is part D telling us? Yeah, all that's changed in part D is that, well, we still get a positive answer, right? We still get 0.15, still positive. So that means it's increasing. If this would have been negative, we would have said decreasing. But here, we're going to say, if we produce $42 cameras, our costs are increasing at $15, right? Because we have to take that multiplied by 100, so $15 per camera. What that kind of is telling us is that, yes, it's going to cost more to produce 42 cameras, right, than it is to produce 24. But the rate at which our costs are going up is less. The rate at which the costs are going up is less. So it might be wise for us to produce more cameras because the more we produce, the less our cost goes up as we produce more. All right, you think you could do a word problem like that? There's one in your homework just like that. Okay? They just use a different cost function, so your derivative is different. They give you 2 points. That they ask you to analyze or interpret the results. And that's what you would see on a test question, right? Something like this. All right, let's do another word problem. This time we'll do price demand. All right, so this example here, price demand. The number of bike helmets people are willing to buy per week from Academy. We'll make it up. Academy Sports. Y'all know what I'm talking about? Academy Sports? Yes? At a price of P dollars is Okay, so I'm about to give you a function, all right? X equals 1,000 minus 60 square root of p plus 25, where p is between 20 and 100. Hmm?
What is P?
What is p? So yeah, that's a great question. Look at the word problem. The number of bike helmets people are willing to buy per week from Academy at a price of p dollars. Okay, so p is the price, all right, and x here is the number of helmets people are willing to buy. Now it doesn't say that here, but from looking at this, you can see that if this is the price, then this must be representative of the number of helmets that they're willing to buy. Now, what does this mean? Our price is going to be between $20 and $100, all right, for our helmets. We're not going to give them away, right? But our helmets are made in China, so you know we build them for $5, right? And then we sell them for 90. We'll see. All right, so there we go. First question. Find dx dp. What is this? Okay. So let's find it first, then we'll talk about what it is, what it represents. So x is a function of p, right? P is our independent variable. This is the variable. This is the function x. So all we need to do is take the derivative of that, right? So can you handle that? Let's rewrite x first. It's 1,000 minus 60 parentheses p plus 25 to the half. I'm doing that so I can use chain rule, right? Rewriting the root as the 1/2. And now derivative time. So dx dp. What do you think?
Start -30.
Yeah, so derivative, this 1,000 we do separately, right? So derivative of that is 0?
Yeah.
Okay, so then we have the negative 60 out here. It's going to come for the ride, and that's because there's multiplication here. So negative 60 times
P plus 20.
1/2, right? Don't forget the 1/2 needs to come out, right? So 1/2. That'll be negative 30. But then I have p plus 25 to the negative 1/2. And then the derivative of what's in here,
1.
which is just 1. Right? Derivative of p is 1. Derivative of 25 is 0. So there is a 1 out here, right? We don't need to write it? Okay. So this becomes negative 30 over p plus 25, but then square root. So all we did here was put these two numbers together, right? Half of 60 is 30, but it's negative. Negative exponent, drop it down, but half power means square root. So this is it.
So you want the answers back in the square.
I think if you're going to wind up plugging numbers into them, for these word problems, we're going to be plugging numbers in. So I would just get it back to something that you're going to be comfortable on your calculator with, because I'm not quite sure how you would do with this. I mean, you might be fine, but some people might mess this up on the calculator. All right, so what is this? What does this give you? What does this function right here give you? It's the derivative, yes. But in terms of the word problem, what does this give you?
They'll give you the price.
Not quite. So let me go back to the graph again. I tried to explain this last time because I thought it would help. Here we have P, right? And then here we have X. What is X measuring, or what is the number of helmets people are willing to buy, right? So this is the number of helmets.
Oh, the cost.
Helmets, right? And then what is P? You said the price, right? Price per helmet. And this is the derivative, right? And the derivative is a slope. And slope is rise over run. So the rise here is helmets, number of helmets, and the run here is the price per helmet, right? So this quantity will always give you the instantaneous rate of change of what? In this case, number of helmets per what? Per price, which is weird, but that's what it is. Per price. So what I'm getting at is that if you understand what x is and you understand what this is, then the derivative will always be this over this. This divided by this. It's a rate. It will be the rate at which the number of helmets is changing as the price changes. All right, so let's try and answer some more questions. Find, for part B, find demand for helmets at price of $75. That's part B.
So we plug it in 75 for the P.
Where the P is?
For the P here? Okay.
So what was dx over dn? What's that equation again?
That's me asking you to find the derivative,
Derivative?
the derivative of this function.
So that's another function, that's another description of derivative.
Yes, that's the Leibniz notation.
The what?
Leibniz notation?
Oh, right, okay.
Yep, we did that last time.
Yeah, right.
All right, so for part B, I think a lot of you are wanting to plug 75 into this. Not quite. Look at what it's asking for. Find the demand for helmets, right, at a price of $75. It's not asking for the rate at which the demand is changing. It's not asking for a rate change, is it? It just wants to know, hey, how many people are going to want to buy the helmets if the price is $75, right? That's what it's asking. Find the demand. How many people want it if you set the price at $75? That's what the original equation tells us, right? You give me the price, I give you how many helmets people want to buy. See, this is part of what makes the word problems challenging on the test. You must be able to read the word problem and know what to do with that information, right? So this is asking us to plug in 75 here. So let's do that, okay? So x equals 1,000 minus 60 times the square root of, now 75 goes in here. So 75 plus 25, right? That's 100. So root 100. So 1,000 minus 60 times 10, because square root of 100 is 10. It's 1,000 minus 600, so 400? 400, what, helmets?
That makes a lot more sense because when I plugged in, because when I thought of that one, I plugged it in and you got 0.3 here. You got, yeah, 0.3. I was like, at $75, someone's going to want 0.3 of a helmet. I was like, that makes no sense.
Just this
Yeah,
slice.
just a slice of it.
Yeah.
That makes a lot more sense.
What's that? I thought I heard something else.
Where'd you get the 10 from?
Square root of 100.
Oh.
I got it. I understand what's going on. Why is it 1,000 minus 60 times 10? Oh, wait, no, 60 times 10.
60 times 10. Yeah, don't do the 1,000. Order of operations, you must do multiplication before subtraction. So you got to do this first. Okay, so if we set our price at 75 bucks, we should expect to have people demand 400 helmets from us, all right, at the retail chain store. Now, part C, want us to find, I'm going to leave that on the board. Part C, find the, how do they word it here? Find the instantaneous rate of change in demand at a price of $75. Now we plug it into the other one. Yeah, so can you see the major difference between the wording of these two questions? This one's just saying, hey, what's the demand at this price? So you just use the price demand equation right here. This one, the key word is this, instantaneous rate, or the keywords are instantaneous rate of change. As soon as you see that, you're thinking derivative, all right? That's what you're thinking. I need to be looking at the derivative. So we're going to plug it into this one now, okay? And let's see what we get. So when we plug in, we get negative 30 over, plug in 75 into this, right? So that's going to be root 100 again? Yes? And that's going to be negative 30 over 10, which is negative 3. I think you forgot to take the root. I thought you said 0.3. Yeah, I think you forgot the root. Right? Yeah. It's all good. All right, so negative 3. Negative 3 what, though? I mean, we need to understand what this number means. Negative 3 what? It's rise over run, right? Which is helmets per price, right? Helmets per price. Now, this is per price is weird. So I'm going to see if I can't help you see it this way. Do you all agree that negative 3 is negative 3 over 1? Is that the same thing? Okay, so I could say negative 3 helmets per what? Per 1 what? How are we measuring our price? In what? Pennies? Dollars, right? Dollars. So $1, right? So this is, you could say, negative 3 helmets per dollar.
Means for each dollar you raise the price, you're going to lose out on 3 sales. So eventually you're going to find the point where it doesn't make sense to do the price.
Yeah, so this is the correct interpretation of this is that at a price of $75, if we set our price for our helmets at $75, then at that instant, any change in price by $1, we should expect a decrease of demand of 3 helmets. So if we go up to $76 on our price, we should expect our demand to come down by 3. Right? And our demand was what, 400? So we increase the price by $1, we should expect to have 397 as our demand. Make sense? Okay. What we'd love to see is like a price that we set where it's going up, right? Where our demand goes up. And so what you could do is you could play with this. Think about what you could do. You could sit here and try and figure out, is there a place where maybe this would be 0? Because then you would be kind of like at the top, if that makes sense. You would have a slope of a tangent line of 0. So if you increase your price, the demand goes down. But if you decrease your price, your demand goes down. So you're at an optimum place. You've got the price set where any change in that price is going to have a decrease in demand. Yeah? We'll do more of this later, don't worry. We're going to do what are called optimization problems. Okay, that's it for this. Okay, you should be able to handle the homework. I'm also going to add to your homework just one problem. I believe on your homework number 91 is on there, is that correct? Yeah, for 11.4. Just add number 93. And on number 93, yeah, I think you can handle number 93. All right, moving along. We're going to go into 11.5.
Oh.
Okay, so we're going to be talking about more derivatives, right? We've built up now. Do you remember when we did derivatives with a limit? Do you remember when we were using the limit? Y'all didn't like that, right? And then I gave you the rules. We had like the power rule, right? We have product rule, quotient rule, we have chain rule, right? Those are the ways we can take derivatives now. We're going to have a new way of doing differentiation that we only want to pull this out when we need it, okay? Only when we need it, because historically, when I've taught this, this is usually where the wheels start wobbling a little bit, right? People have trouble with implicit differentiation. It's just, that's the nature of it, all right? So let me start with a basic example first. Let's start with y equals x squared. And let me ask you to find y prime. Now this is not a trick question, okay? This is not a trick question. So what is it? Y prime is 2x. Agreed? And we're happy? Yes? Y prime is 2x. Now, I'd like for us to look at this problem a little different. What if I had written y minus x squared equals 0? Is that the same problem as this? Is that the same equation? Yeah, all I've done is move the x squared to the other side, right? So subtract x squared here, subtract x squared here, you'll get a 0 on the right side and you'll get minus x squared here, yes? Now, I would like for us to still do the same thing. Find y prime. But I'm going to add a little thing here. You're not allowed to move anything around now. Okay, you can't move that x squared back over. Okay? Can't do that. So how can we get to this same answer? Well, what we do is this thing called implicit differentiation. And what we're going to do is we're going to take the derivative on both sides of the equation. Like you may not have even thought about that when you were doing this, that you were actually doing the same thing. We took the derivative of y. What's the derivative of y? Y prime. What's the derivative of x squared? 2x. Do you see how you can almost look at it like we did the derivative on both sides? Okay, let's do that over here. What's the derivative of y? Y prime minus, because I can do these separately, right? What's the derivative of x squared? 2x. And then what's the derivative of 0? Well, 0 is a constant, right? So derivative of a constant is still 0. And now, could you just move this over and you would have the same answer? Yes? Yeah? Sure? I'm just showing you a different way we could do this. That's all I'm showing you. And I'm sure you're sitting there going, well, why in the world would I want to do that, right? Like, why would I do this if I can do this, right? Okay, so let's try this now. New problem. Let's look at yx minus x squared equals y squared. Okay, look at that equation right there. I want us to find y prime. So what I'd like to point out is, do you agree with me that in this first equation, we had it solved for y? Like we had y by itself, and then we just took derivative of this side, and we were done, right? If you look at this equation right here, it is not possible to get y by itself. You can't just move things around and get y by itself alone, all right? And because of that, you can't take the derivative this way. So there are certain equations we may come across where you can't isolate one of the variables. And so you have to have a different method. So we do this implicit differentiation. You ready for it? Because this one's going to be a little bit messy. You sure? You ready? No? Okay, well, at least you're honest. Okay, here we go. Sir, you got something going on. You've been on that phone the whole class, but I'm afraid that if you don't see this, you will fail the next test for sure. All right? All right, so we've got to take a derivative. We're going to do derivative on this side and this side separately, right? Over here, minus between them, right? So we can do these individually. Yes? So let's start with this. We have to take derivative of that. How? Can we just do derivative of each one separately? It's a freaking product though, right? We don't do products individually. What do we do when we see products? What rule do we do? The product rule, don't we? So we have to take derivative of this using the product rule. Now the product rule, remember, product rule said this: if you had two things multiplied, the derivative was f prime g plus g prime f. And what I was really trying to get you to see in that product rule was that when you do a product rule, it's the derivative of this one, right? Then times this one, plus the derivative of this one, then times that one. It's like they trade places. I need to do that here. So let's see if you can't help me walk through this. I'm doing product rule. There's my product right there. What is the derivative of this one? Y prime. Times, now this one, do I take the derivative or not? No, I do not. Times x. Right? So all I've done this part. Now what? Plus. Now, the derivative of x. What's the derivative of x? 1. Right? Derivative of x is 1? Derivative of x is 1? Okay. So 1 times what? Y. This one, but I'm not taking the derivative. So that is the product rule on that piece. See it? That right there is just that.
So why wouldn't you just put the x and the prime the way you did with the y?
Why wouldn't I do the what?
The x with
Like x prime?
x prime.
Okay, because, that's a great question. Because the derivative of x for us has always been 1, hasn't it? Right? So when we're saying find y prime, we're really saying find dy dx. And so we're treating x like our variable, so the derivative of x is 1. But the derivative of y is not 1. The derivative of y is y prime. It's tricky. It's tricky.
As a variable.
Yeah. Does that clarify that a little bit? Okay. Now, I'm done with the derivative of this. Okay? I'm done with that. Now I move on. Minus. Now, what's derivative of x squared? That's just 2x. There's no change in that, okay? 2x. Now I write my equal sign. Now here's the one that's really tricky. Y squared. What's the derivative of y squared? 2y seems like a very natural response, right? And that so far is good. Okay, but it's not complete. It's 2y. And then times, I'll show you why this is this way in a second, times y prime. What the hell? What happened just there? What happened? Well, here's what happened. This right here, y squared, we're really looking at that as being like this right here is like our g. In the chain rule, remember the chain rule says if you have g and you have a power, the power comes down, then you don't touch it to the first power, right? 2 comes down, don't touch this to the first power. And then the chain rule says then take derivative of what's in here. And what's derivative of y? Y prime. Do you see that y prime is coming out from the chain rule? That does not happen with the x though. With the x, derivative of x squared, boom, just 2x, you're done. But this one, you have the 2y and then the y prime that pops out. Yes or no?
Which y became the y prime, the first y? Or the last?
Okay, let me go back to this. That's a squared. Let me fix it. Okay, if I asked you to take derivative of this, right? You would go 3 comes out. You wouldn't touch this, right? 7x squared plus 1 there. And then you would take derivative of what's in here.